We're starting EDCON Hack Workshop again today. Today we have Luke Anderson, co-founder of Sigma Prime. He will be talking about anatomy of a client. He will be doing an overview of different components that work together to form an Ethereum client implementation. He will also identify for you the different components and provide example of each in both Eth1 and Eth2.0 context. Luke, it's all yours, guys. So you will have opportunity to ask questions during and at the end of the workshop. Please use chat for this, and please send message to everyone. You have a chat button underneath your screen. Thank you. And Luke, it's all yours now.
Hi, everyone.
How are you?
So I've put together a few slides just to talk. So I was asked to do this workshop on clients, probably because we're building a client for Ethereum 2.0 at the moment, and so I wanted to just give people a bit of an overview, a bit of an introduction into what the components are, how everything fits together when we're building a blockchain client, and some of the considerations for it. And so I called this workshop Anatomy of a Client. So that's what we're going to be talking about. But first of all, who are we? So as some of you may know us, we're called Sigma Prime. We do we typically have a background in information security. We've been doing that for quite a while now, and we moved into smart contract auditing and security reviews, and then we decided that, well, while it's really fun to break people's code, it's also fun to build things, and so we decided to build a client for Ethereum 2.0, which we called Lighthouse, and it's been fun. We've been building that in Rust, and that's all on GitHub and open source. You can see the link down there on my slides. So as I work through this, I'm happy for you guys to. I know you can't speak in here, so if you want to chuck your questions into the chat, just whenever you're ready, I'm happy to have this bit more of an interactive session and answer your questions as we go. And yeah, I'll read the question out loud, and then we'll answer it. So when we talk about a blockchain client, like, at the end of the day, we're building a piece of software, right? We're building a piece of software, and like most pieces of software, we have to interact with the real world. And so, of course, in order to run the software, we need some kind of command line interface for it to be useful. We need to have an application interface. It needs to be able to work on every platform, even Windows, probably especially Windows. We need to be able to save state. We need some kind of database. It needs to be persistent. And of course, in a blockchain system, we need to be able to interact with all of the other nodes in our network. We're also going to talk a little bit about the specification. The specification is really important because that's what tries to keep everyone on the same page to sort of know what we're working towards. And we're also going to talk a little bit about the consensus duties that these things have. So the things that I sort of assume that everyone has a decent understanding of is that they've used Ethereum 1.0 or 1.x, and that you know that Ethereum 2.0 is a thing. I don't expect you to know all of the ins and outs of it, but at least knowing that it has proof of stake, where validators can deposit Ethereum in the Eth1.0 chain. And it also has sharding, where it's like having 1,024 Ethereum chains, all coordinated by one central beacon chain. And so I've prepared this diagram, which is a bit of an overview of what I think the components are. I've kind of separated into two halves here, where everything on this sort of side is the real world, and then everything on this sort of side is the actual client software, right? Because at the end of the day, we're writing software to interact with the real world and to support our efforts in the real world. So I think it's important to make that distinction. And so, of course, in that real world, we have, the user, right? The person who is interacting with the blockchain, who's interacting with our client. And the first thing they need to be able to do is actually run the software. And so how they run the software using our command line interface is really important. options there are, configurations there are. So as I go through this section is sort of an overview of how it's all structured, and then we're going to start deep diving into some of these areas with a bit more detail after this. So of course our user needs to run our software using the command line, and maybe they also need to actually manage their keys. And so most clients will also support some kind of wallet interface to be managing their Ethereum private keys, so manage their Ether and that sort of stuff. And while it's all well and good to be, running the client and managing our wallets, the ultimate goal here is, of course, to allow users to have much more vivid interactions and interact with decentralized applications, or dApps. And of course, dApps, being a program, need an application programming interface, an API, and maybe they also need to help users manage their funds as well. Right, okay, so that's sort of our users. So the other kind of section of a client, I think, is the networking layer. And of course, a blockchain client doesn't run on its own. We need blockchain clients to talk to each other online. And so we have two major components that I see in the networking layer. The first one being discovery, where we actually need to go into our peer-to-peer network and find out who's out there. Right? How do we find who we want to connect to? How do we know what they're capable of? And that sort of stuff. And then once we actually discover some peers in our network, we actually need to talk to them. And so we need to know how to talk to them, and they need to know how to talk to us. And so we call that the wire protocol. And the wire protocol allows us to do things like syncing, sending blocks around, and that sort of stuff. So that's the kind of interactive layers of the like a blockchain client, with the network and of course with the users. But the other major part I've put down here is the spec, right? And the spec down here is it's the thing that gets everyone in sync in the first place. It's sort of the rules of the blockchain, and the spec mainly governs all of these parts over here. Including the fork choice rules, block processing rules, so what makes a good block, what do we need to do, and very importantly, the spec usually defines a set of tests, and these tests make sure that every single client is on the same page, so that when we actually launch them into a global blockchain network, that they already know how to talk to each other, and we've already verified that they're capable of doing so. The other part that the spec kind of helps denote is what I've called the consensus agent. Now, that's sort of a general term for the miner, right? In Eth1.0, it's the miner. In Eth2.0, it's the validators. And so I've split that into two sort of parts here, signing and duties. But this component is still very much governed by the specification, which we'll talk about more in a minute. And so, of course, we've got all these different components all working together to form the blockchain client. And well, they're certainly not stateless. So when we discover new peers, we want to be able to save those peers and actually write them into our database. As we listen to the network and we receive new blocks and new transactions, we need to store those somewhere in some kind of cache so that we can then maybe do our block processing up here and then store them into some kind of state tree that's on disk, so we don't need to resync every time we turn the node on. Further, while the miner doesn't have too much to store except for what's called the DAG, the validators down here in the consensus component, they need to make sure that they don't double sign conflicting blocks. So if a validator can sign two different things that conflict, then they get slashed, i.e. they lose money in proof of stake. And so they need to make sure that they maintain state so that they don't ever commit that sort of felony. And they also need to manage when they're expected to do things, right? So they need to keep sort of a log in their own little calendar of when they need to do stuff. Okay, so I'm gonna start now by drilling down into each of these components. And I also just want to mention, I think I put it at the end of these slides. There's a really good talk from DevCon 3 in Mexico that's quite similar to this, and it talks about the anatomy of a client. I mean, it's a couple of years old, and it's talking mostly about Ethereum 1.0, but that was also a really good talk that I modeled some of this talk off. So let's talk about the interfaces first of all. So, I mean, interfaces are of course very important because that's how someone interacts with our software in the first place. And running the software on the command line, right? So our command line interface here is it's really important to get that right, because in a blockchain client, you can have a huge number of different configuration options, some of which we're going to talk about soon. And being able to specify, concise, succinct configuration files for these is really, really important. And so Geth actually has a dump config command. If we look down here, there's dump config there, and it will actually output a YAML file for Geth with all of the different options available that allow you to configure it. And that means that we can try and be a bit more concise with what we do. So handling configuration files is a really important part of it. It also helps when we want to start doing deployment with Docker and these sorts of things. We can start versioning those. Of course, actually dealing with flags, which I've mentioned here, like command line flags that we're all used to, is important as well. And there's a bunch of libraries to help with this. So the ones that I've pulled up here are from Rust, because I mean, what we're building is in Rust, but Clap, for example, is a way to manage and handle different flags and optional flags and all that sort of stuff on the command line. As you can see here, it handles the short flag version versus the long flag version, what's it supposed to do, the help file, and all this sort of stuff. And of course, it is really important to have help in these as well, because there's often a huge number of configuration options in these, and we need to be able to describe and discern between the different ones. The other thing I've mentioned here is in the CLI is logging, right? So since we're running a command line piece of software, it's very important to make sure that our logs are really sensible and easy to digest. You'll notice that different clients deal with this in different ways. Some, go as far to make sure there's nice, pretty colors in there, and that they sync up, and they give lots and lots of regular pieces of information, and that's quite good. Make sure you don't reinvent the wheel though, and just use print statements. Instead, use something like, so in Rust we've got this thing called slog. It actually is it gives us sort of a structured output, and it means that if you're outputting something from some function inside another function, it will actually create the indentations for you. It's going to create the colors in the command line as well for you. Plus as well, it really helps us to manage different levels of logging as well, right? So sometimes you want to show debug logs, sometimes you want to show it's just like a little bit of information, sometimes it's a critical error, okay? And our logging library, as I'll call it, it goes a long way to help with that, and that really makes a big difference for the developer experience, because of course that's our sort of main interface at the moment. The other big interface and the reason I put this as a separate sort of point here is that a lot of the clients include the wallet as its own piece of functionality. For example, Parity has, so you can run the Parity client and it can interact and go and pull find the wallets on disk and interact with those wallets through the personal API. But it actually, in order to manipulate wallets, generate new accounts, you run Parity in a sort of a standalone mode, like Parity space account space new or something like that. And the ability to manage this wallet being sort of a separate functionality is quite important, because it keeps a lot of the critical operations out of the main blockchain client. And that's got that's got a few different reasons. For me, one of them is keeping the functionality separate so that if there is some kind of vulnerability in our client, some kind of exploit, that's not going to allow the attacker to actually get down and edit our accounts or God forbid, print out our private keys in raw format. The wallet also really needs to make sure that we're handling the data on disk securely. So if for anyone who's played around with Geth and has opened up their private key files on disk, they'll notice that it's actually a JSON file, and it's got, saying, oh, we're AES in, I don't know, CBC mode, and here's the hash and all that sort of stuff. And so having storing that on disk in a sensible way is really important. Another part of the wallet, I mean, this point kind of belongs in sort of throughout the whole blockchain client, but I mentioned here in the wallet, is also secure handling of data. An example of this is zeroing out memory. So when in a computer, when you delete data, it doesn't actually get rid of the data. I'm sure most of you understand that when you delete a file, it just marks that space as unused so that it can then be used again in the future. This is true for memory management in software as well. So that if I, free a pointer to some piece of memory and that's not used, that's now free memory, that's all well and good. But that actual physical piece of memory still contains the data. This means that if someone can do some reverse engineering, if someone can get root shell on a machine and dump the memory, then they can actually still see that sensitive data inside the memory, even though it's not being used anymore. And so it's really important for any blockchain client to go through and zero out, actually write zeros or write random data to any piece of memory that has been used to store things like cryptographic keys or anything sensitive. The third part I've included here as part of the interface is the API. And of course, this is, so there's sort of our user experience and our developer experience. CLI is kind of a little bit between both, but the API is, of course, really important to get our developer experience right. I think this is almost the most important in a way, because at the stage that Ethereum is at right now, that we're trying to get more development, we're trying to get more support in the developer community, that making a really clean, easy developer experience is really, really important, and I think it grows the ecosystem a lot when a developer can come on and get working with something within 5 minutes. And so this is for things like dApps to interact with, like MetaMask plugin in your browser to talk to, and all this sort of stuff. There's two sort of major parts to this. There's the specification around the API that says, okay, well, this is how you can talk to us, and this is, what we're going to do. And then there's also the serialization side of things. And so in Eth1.0, it's called the RPC, or usually it's called the JSON RPC, and that's sort of saying, okay, well, the RPC stands for remote procedure call, and JSON is our serialization format. And so to interact with Ethereum 1.0, you typically send HTTP or WebSockets requests to the client, which are JSON encoded messages. In Ethereum 2.0, we've decided to move to something a little bit more sophisticated, and that's called gRPC. gRPC was invented by Google, and while there is a little bit of a debate around whether or not we should be using Google software in Ethereum 2.0, it is actually a very, very fast API sort of library, which is used all across the internet by very large websites. It's very efficient, and it doesn't use JSON as a serialized format. It also doesn't use HTTP or WebSockets because they have too much overhead. And so instead, we stick with gRPC, and its serialization format is called proto buffer, or I think it's protocol buffer or something. And that's a structured serialization format specifically used by gRPC. Another point that I haven't listed here that I really want to mention is documentation. Of course, interfaces, in order to actually interact with the API, CLI, well, any of that, our documentation is almost the first interface that anyone deals with. And so getting our documentation really clear and really concise I mean, I shouldn't have I should have even put it in on this slide here. It is probably the most important interface that your blockchain client will have. And so something that you might think is missing, where's the graphical interface? That's an interface too, right? And while it certainly is, I'm not going to spend a lot of time on that because I don't think that a graphical interface is a really important part of an Ethereum blockchain client. Ethereum blockchain client is, in my mind, a back-end piece of software that should not have a graphical interface. Now, that's not to say that there doesn't exist graphical interfaces. In Geth, in Go Ethereum, Mist is the graphical interface of choice. It's been around for a long time. Yeah, I see Peter says EOS has a GUI, and I believe that. And Parity also used to have a GUI, but they deprecated it. And I think I've got a typo there. That :W is my Vim trying to write, so you can ignore that. But the Parity UI is actually been deprecated now. Oh, it was a joke from Peter. So EOS doesn't have a GUI. There you go. I haven't actually used EOS, so I wouldn't know. But Parity UI, they used to have that web interface that you could go in and you could add different accounts and interact with smart contracts. And honestly, I thought it was really cool. I really enjoyed that a lot more than Mist. But they've deprecated it. They don't support it anymore. They've still got it if you want to use it, but it's been retired. And I think a big part of that is that it takes a lot to maintain a graphical user interface, and it's very much a different skill set and has a really different set of priorities to what an Ethereum client does. So I'm just reading the question from Singali there. I might come back to that question a little bit later if that's okay. And so finally here as well with the graphical interface, of course, Ethereum 2.0, don't hold your breath on any graphical interface. I don't think we'll be seeing any of those anytime soon. But fingers crossed. And so the next sort of component that I wanted to talk about is, of course, the interactions with the peer-to-peer network, right? A blockchain client doesn't sit there and it doesn't sit in isolation. It's got to talk to nodes all around the world, other instances of its software. And of course, not just instances of itself, but other implementations of the same specification, which we'll talk about in a minute as well. So I sort of separated this into two major components: discovery and wire protocol. And so discovery is the process by which we find other peers in the network. And the reason we need to do this is because we can't just, we need a specific protocol around this because we can't just broadcast. When we plug into a local area network, we can plug in and we can kind of do a DHCP broadcast of the whole net. We can actually talk to every single node in the network quite easily because it's quite isolated. But of course, in blockchain systems, we're actually creating, where the internet is our base layer, we're creating a sort of a layered network on top of that. And so we have nodes all over the world, and we need to find which nodes have which IP address, what we can talk to, how we can talk to them, and where they are. So to start this process, there's usually a set of bootstrap nodes that are hard-coded into a client. And there's been, so if I click on that there, I've got an extract here from the Go Ethereum bootnodes.go file, and you can see here's a set of mainnet boot nodes here in their enode URL, which I'll talk more about later. You can see that there's some C++ clients here. There's a bunch of Go clients here in Ireland, Australia, Singapore, Germany, and that sort of stuff. And you can see there's different ones here. There's some for testnets, Rinkeby. Different networks have their own boot nodes. And so the idea of these boot nodes is that they're sort of the first port of call. They're like a long-running client that someone keeps online at all times, and often the boot nodes don't even participate in the wire protocol. You can't even ask them for network information. Their sole purpose is to respond to your initialization boot node request and then give you more nodes to connect to around the world. The algorithm that this is based on is called Kademlia. Now, Ethereum uses a modification of Kademlia, but it's quite closely related. And Kademlia has been around. Here's the Wikipedia page on it. Has been around for a long time. It came out with. It was the one behind. Was it LimeWire? I can't remember which one it is now. But some of those big. Here we are. The CAD network, of course, it uses Ethereum there. Gutenilla, that's the one I was thinking of here, used by LimeWire and that sort of stuff. And so that's a peer-to-peer network discovery protocol. It's been around for a while and is quite well understood. Now, newer versions of blockchain systems try to use a concept called topics. And so while it's great to be able to find nodes on a network that are of course on your network, different nodes might interact with you in different ways. For example, some nodes might be currently syncing. They might not have the full blockchain, so you can't ask them for for very recent data. Whereas other nodes are maybe fully synced and ready to go. You can ask them for the latest updates. Or maybe some nodes participate in IPFS or some kind of file storage protocol, and other nodes don't. And so in the latest, in the even recent versions of Ethereum 1.0, we have Discovery version 5. And as you can see here, this is a package, a Go package, all about Discovery version 5 for Ethereum 1.0. And this talks about the different topics, how we manage different topics. So you can see here that there's a register topic, and here register topic, and search topic here that allows us to actually ask parts of the network for, hey, who's ready to talk to me about cats or something like that. The new Ethereum 2.0 is definitely going to be using topics in the discovery protocol. This is also going to be a big part of this, is to discern which nodes are interacting on which shards. So because we've taken the Ethereum network and split it into 1,000 shards, well, some nodes might only know about shard 5 and shard 26, right? And then other nodes might know different shards. So we need to be able to connect to nodes that are actually synchronizing with the shard that we're most interested in. And so we're obviously collecting a lot of data here around who we can talk to, how we can talk to them, where are our nodes, and all that sort of stuff. And so it's really important for us to be able to remember our peers, and that's why I've just put the database icon down here, because the discovery protocol typically writes the nodes that is seen and the Kademlia buckets that it puts it into some sort of persistent file. Otherwise, every time we turn our node on, we've got to go start talking to the bootstrap nodes again and start all over again. So it is important to save the nodes that we discover. The other big part of networking is, of course, the wire protocol. It's great to find the peers, but we now actually need to talk to the peers, and how do we actually interact with them? And so in Ethereum 1.0, we use this thing called Dev P2P. And Dev P2P is a protocol, so it's sort of a framework for sub-protocols, right? And I'll get into what I mean by that in just a moment. But the actual protocol itself and how we talk to different nodes is on an encrypted transport called RLPX, right? And so RLPX is how we actually talk, how do we do the encryption and all sorts of stuff, how do we do handshakes, authentication, and that sort of stuff, right? It's where we start talking about node keys and node IDs, which I'll go into in a little bit. And so on top of RLPX, on top of our sort of encrypted transport layer, which generally, by the way, runs on TCP, the Dev P2P supports some basic protocol messages, and then a series of sub protocols. And so I've linked here to the Ethereum wire protocol, which is, as it says here, actually a sub protocol of dev P2P, right? And then this sub protocol here allows us to do things like, get block hashes and get blocks, and here's a new block, and get block headers, all of this sort of stuff. And this wire protocol here defines how we actually talk to other nodes. What can I ask another node, and what's it going to give back to me, or what is it at least supposed to give back to me? If I look at the dev P2P specification, you can see here. Oh no, it's not here. Doesn't matter. Either way, the Ethereum protocol is just one sub protocol that is available on the dev P2P sort of framework. So this is still very much a work in progress for Ethereum 2.0. Ethereum 2.0 we have not settled on a wire protocol yet. Everyone's still kind of trying to nut out what needs to be transferred, how it needs to be transferred, and all that sort of stuff. And so I feel like the wire protocol will be one of the last things to be solidified. So while the spec is still very much changing, where I think that once the changes start slowing down on the spec, we'll be able to nail down a consistent wire protocol. And I've also mentioned just want to mention here as well that it's important to be able to cache all of the messages that come in on the wire. So an example of this will be the sort of unconfirmed transactions. As we're listening to the network, we'll hear about all of random transactions that'll come in from all over the network, and we need to actually be able to sort of save those into some kind of cache where we can process them later or look them up. And that does not need to be persistent. So as we're talking on the network, if we hear about an unspent transaction, we don't need to write that to disk. We just need to kind of hold it in memory until we're actually ready to process it. I've just got a slide here as well on node IDs. How do we actually identify everyone in the network? We do that through the use of a public key called a node ID or a node key. And this is this is part of the RLPX encrypted transport protocol. This has got nothing to do with Ethereum keys, nothing to do with Ethereum private keys, and it's actually when you first instantiate a client, when you first turn it on or install it, it will randomly generate a new private key, which of course has a corresponding public key. And that data forms part of what's called your eNode, Ethereum node URL format, which I've listed down the bottom here. So you can see, so I've shortened it because it's a very, very long key, but here at the start is the Ethereum, the node ID for some particular eNode, and that is, as I said, it is the public key for the node. So that when I start talking to that node, I already know its eNode URL. I know its IP address, which is also listed here. I know it's the port that it's listening on, and maybe even if it has a different discovery port that it's listening on. But I also know the public key that I'm going to talk to it, right? Because this is the public key here. And so that when I start talking to it and it starts sending me encrypted and signed messages, I already know how to verify them. Now, actually connecting to all of the nodes in the network, you can discover the whole network. And even if you saw the whole network, most nodes you can't actually connect directly to because of network address translation. I won't go into the details of what that is, but network address translation is it sort of hides everyone behind their firewalls. And in my experience, I've actually scanned the whole Ethereum network before. In my experience, only about 20 to 30% of nodes were actually directly contactable. Another thing I wanted to just link to here as well is that the Ethereum node IDs actually leak data in a way because you're moving around the network and maybe you're moving around the world and you're maintaining the same node key, say it's installed on your laptop. this talk here by Peter from Geth at DevCon 4 at the end of last year talks about how, if someone takes their laptop from Berlin to Prague, we can see that their IP address changes, and we can actually track individual nodes as they move around the world. So there are definitely privacy concerns related to node IDs as well, and that's, in my opinion, a very difficult problem to solve. Does anyone have any questions at this stage? If you do, chuck them into the chat, and I'll try and deal with them. The next part I want to talk about is is the spec, and I say the spec with a little sort of laugh in my voice, because in our team we've been dealing with the spec a lot lately. As we've been trying to build a client, the spec has been kind of changing on us. And so in Ethereum 1.0, the specification was sort of written before Ethereum was ever launched. Or of course it has to be written before it was launched, and that came in the form of Gavin Wood's Ethereum yellow paper. And so the yellow paper, unlike the white paper, is a very rigorous specification of what's going on in how to talk about everything. What's the balance, what's the storage route, code hashes, and this particular specification is, while it's very detailed, it can be very hard for some people to digest. This is a very formal and academic style of specification, which has some benefits. And this is also, for those who are curious, this is also where the name Sigma Prime actually comes from, is this here, the world state in the Ethereum yellow paper. In Ethereum 2.0, we don't have this sort of really academic formal specification. Instead, it's a bit more wordy, a bit more, and so this is it on GitHub here, published by the Ethereum Foundation, of course, and it's a bit more wordy, a bit more developer friendly, I would say, right? It's tables and a bit more straightforward. Eventually, this specification is actually going to get turned into what's going to be called an executable spec, whereby it's actually going to be a specification written in Python or something like that, rather than this sort of big wordy document. The beacon chain, the phase 0, is the main spec that we have spent most of our time on right now. But the other part of this is the phase 1 spec as well, which is sort of coming in future. That's kind of once we think about sharding and all that sort of stuff. There's other specs to deal with here as well, like the simple serialization spec, BLS signatures, and all that sort of stuff. They each have their own specs. And so the reason the specification is important is it's kind of the canonical source of truth for how a client actually is supposed to work, right? And so there's all kinds of blockchain logic that is defined in that specification. And so I'm going to talk about some of those blockchain logic components. I broke it down into three major parts here: fork choice, block processing, and consensus tests are the things I want to talk about here. So fork choice, first of all, if you're interested in finding out more about this, we actually published a blog article on this recently on the Lighthouse Sigma Prime blog, and we actually talk about what a fork choice is, what it means in Serenity, and how it all sort of works. But to give a quick overview of that, it's basically a decision-making process of how what block should we actually agree on? What's the correct block? What does a correct block actually look like? And in Ethereum 1.0, that's pretty easy, right? In Ethereum 1.0, we have the highest total difficulty, right? And in this case, so the proof of work function, right, has a difficulty. There's a certain amount of difficulty that goes into creating each block, right? And so the correct block is the one that has the most difficulty behind it, right? And so the total difficulty field that you'll see on Etherscan or whenever you look at a block is kind of the sum of the difficulty of all blocks before it, right? And that is basically another way of saying the longest chain, right? Now that makes sense in a proof of work context, but since there's no actual work that has to go into extending a chain in proof of stake, it no longer makes sense to just follow the longest chain. If you're following the longest chain, I could just stake and sign a whole bunch of blocks and just make it super, super long, and you'll believe me. So that's not going to work. And so we've come up with new algorithms for fork choice rules. The latest one I know of is LMD Ghost, which stands for Latest Message Driven Greediest Heaviest Observed Subtree, which is a serious mouthful. And this, I'm not going to go into the details of it here, but there is a link to the LMD Ghost stuff, as you can see in the beacon chain specification here, right? And there's a bunch of details and a very naive implementation here as well to check out. So fork choice is an important part of the spec and, of course, of the blockchain logic. The other important part is actually dealing with blocks. Right, so when we get a block in from the network, or when we might create or mine a block ourselves, we need to actually validate, is this block correct? So, the most basic check in a proof of work system is, does the hash of my block satisfy the proof of work requirement? So in Bitcoin, does it have enough zeros at the start of the block hash, for example? It also means checking any signatures are correct, that the fields all make sense. Basically, just does this block actually make any sense? We're not introducing something wrong here. State transitions is, and I mean, I've got one sort of point here of state transitions, but this is actually a huge topic in itself. And it's mostly about the Ethereum virtual machine and about the way in which we process transactions and manage the state, right? So when I call a contract, the state of that contract changes. We need to be able to calculate what the new state is, okay? And so in Ethereum 1.0, the EVM, the Ethereum virtual machine, is the way that we do that. It's a way to interpret that sort of compiled bytecode to perform the state changes. In Ethereum 2.0, we're looking at EWASM. EWASM is the Ethereum flavored WebAssembly. It's basically an alternative to the EVM and a completely different way of representing smart contracts and logic. But just like Ethereum 1.0, Ethereum 2.0 will have a state transition function as well. And it's kind of part of the state transition, but I've mentioned it here separately as the sort of accounting components. And accounting is kind of things like making sure that the nonce value, so every account in Ethereum 1.0 has a nonce. Every time I send a transaction, that nonce is increased. So making sure that the transactions that come in are have the correct nonce value, that if I've lost money or gained money, that my balance is updated. In Ethereum 2.0, we're going to have validation and validators, and so of course those validators and stuff need to be actually rewarded, penalized, and their balances updated, and all that sort of stuff as well. And so the other part I wanted to mention about the blockchain logic is because there's actually a lot of content behind this, and there's a lot of functionality going on here. How do we make sure that when we launch our network that it's correct, right, and that we are absolutely all on the same page? Well, the specification usually also publish a set of tests, right? And so for Ethereum 1.0, there's a huge set of tests here seen on GitHub with all kinds of different things that can be applied to the Go client and Parity client, Trinity, etc. And so the idea is that every client passes all of these tests, and therefore they should all be able to talk to each other. Ethereum 2.0 has a similar concept. The test vectors, which is it's obviously Eth2.0 hasn't been around as long, so it's a bit more simplistic at this stage. But it's really important to make sure that our client conforms with these tests. I just wanted to have a quick mention here as well that there's all that functionality that I've just spoken about, there's a huge amount of configuration and different options that we can take in this. We can do different types of syncing. Are we, storing everything? Are we going to compute everything? Are we going to try and have a light client? Are we going to be on the main net? Are we going to be on Ropsten or Rinkeby test nets? And if we have a quick look here, I'm not even going to open it. It takes too long to open. But there it is, the big JSON file here. This is the parity Ethereum JSON configuration file. And as you can see, it is a huge file full of stuff, including all of the balances that came out in the launch of Ethereum. So there's a lot of configuration around this blockchain logic that we need to manage, which is also why I mentioned configuration files in the beginning. The next component I wanted to talk about is what I call the consensus agent. And that's I tried to come up with a general term for what in Ethereum 1.0 is a miner and in Ethereum 2.0 is a validator. And this is kind of a separate component from the blockchain logic in a sense, because it is somewhat optional. You don't need to run a consensus agent in order to interact with the network. And they also have pretty different requirements. A miner, of course, needs to be able to collect transactions in order to create a block, or at least perform the proof of work algorithm on a block. The proof of work in Ethereum 1.0 is Ethash. And Ethash looks up, it also needs storage because it looks up what's called the DAG, or directed acyclic graph. These are usually, graphics cards and maybe ASIC miners and that kind of thing that run miners in Ethereum 1.0, as we know. In Ethereum 2.0, our consensus agent is a very different beast. In that case, of course, we're getting away from proof of work and we're going to proof of stake, and so we need to have validators in place of miners in this case. Now, one of the very big differences in my mind between the two is that a validator actually needs to handle encryption keys. Right? A validator digitally signs data, proposed blocks, attestations, these kinds of things. And because it needs to handle cryptographic keys, and those cryptographic keys are actual Ethereum keys, they hold money, they're related to the stake. We need to sort of lock down this client a bit better. We can't just sort of spin it up on a machine and hope for the best, which with a miner in Ethereum 1, you can do. A miner in Ethereum 1 does not perform any cryptographic operations really, apart from, a hash function. It doesn't need to do any digital signing, doesn't need a private key, whereas a validator in Ethereum 2.0 does. So it has very different requirements in that sense. A validator in Ethereum 2.0 also has a much more strict requirements on what it does when. Right? It has very clear duties that it must perform at particular times. And so while I've sort of represented digitally signing here as a signature, I've represented its duties as a calendar, because that's kind of what it does. The validator needs to maintain sort of a calendar of which slot I am going to perform which action. And when I say slot, if you're wondering what does he mean by a slot, take a look at the Ethereum 2.0 spec terminology here, and you'll see that a slot is a period during which one proposer has the ability to create a beacon chain block, and some attesters have ability to make attestations. So basically, these are the things that you need to do at a particular point in time as a validator. They're your responsibilities or duties. And so we have all these different components, and of course, all these different components need to actually store data. I've already mentioned a few times that they need to either cache data or store it more persistently. And so I just wanted to mention the data storage components here, where we have our sort of 2-disk data storage that's very persistent, and our cache, which may be very ephemeral. Things like network peers, all of the block headers, and the state trees are very important to store. That's kind of obvious. And another one that I put here as well is signed data. So the validator, if it signs block A, then it can't sign any conflicting block, right? So if it signs 2 messages that are actually conflicting, then that validator gets slashed. Right, this guy here, right? So when it digitally signs the data, it needs to make sure that it never signs something that conflicts. So if I run my validator, it's signing stuff, and then I shut it down, and then I turn it on again, it needs to make sure it still knows about all the things that it had previously signed so that it doesn't create a slashing condition. There's a lot of other things that we don't necessarily need to save to disk, like the unconfirmed transactions that are floating down the network, different forks and different blocks that we might have heard from different people that we don't necessarily include in our chain, looking up the state of different variables as we're doing calculations, and maybe our duties calendar as it comes along as well. And so these two different types of storage have very different requirements. And of course, the persistent database really needs to be able to save things to disk in a really reliable way. Two examples I've got here are LevelDB and RocksDB. I think RocksDB actually sort of came from LevelDB, which was developed at Google. LevelDB is a Go implementation. This is what Go Ethereum uses as its on-disk storage mechanism. And these are almost, for pretty much all Ethereum clients, these are key value storage systems, right? There's no SQL or structured data here. It's just kind of like key value. There it is in the disk. And different implementations have some different trade-offs as well. Just in my experience, I know that when we used to do mining many years ago now, that we tried with both Geth and with parity, and we found that while parity was nice and fast and we really liked it, anytime you would lose power to the miner, which doing it at our homes was actually more common than you might think, that sort of rapid loss in power would cause parity to corrupt this database very quickly. You'll notice that if you ever run parity and you press Control-C, it says finishing work, please wait, and then it shuts down. And that's where it wraps up all its threads and makes sure everything's written to disk and closes. If you don't do that, it gets corrupted data and parity doesn't boot up again properly. Geth, on the other hand, it seemed to be a lot more tolerant to power failures for whatever reason. The way it stored data meant that it wouldn't end up corrupting itself if that sort of happened. So considering what storage mechanism we use for what is actually really important, depending on what we're trying to achieve. And I think that's pretty much the end of my slides. So I've put a bunch of links throughout the presentation to different references and things that you should check out. I will post a link to this slides. In fact, I will do that immediately in the chat. Oh no, that's not everyone. I want to talk to everyone. There we go. There's a link to these slides, and there's also a talk. So at DevCon 3 in Mexico here. So this is in a playlist with all of the ones from that day in Mexico. Is another talk, basically anatomy of Ethereum clients. So if you found what I had to say interesting, then you might want to also listen to this one as well if you're interested. Otherwise, that's all I got to say. And if anyone has any questions, I'll stick around here for the next however long. And otherwise, I think I'm at time. Thanks, Darren and Zhao King. I think I'm saying that right. And James. Thanks, guys.
Okay, thank you, Luke. So while you guys thinking on your questions, if you have ones, please type in the chat. And in the meantime, we're going to announce another workshop, which will be in a few days, March 7. That will be about building your first state channel by Trevor Clark. And in this workshop, you will learn how to build your first state channel. We also have all these links on the screen displayed for you to sign up for the hackathon. And to remind you, this workshop was created by EDCON Hackathon Organization Group, by CryptoChicks and LinkTime. Please sign up for the hackathon at ethcon.io/hackathon and follow us on social media, and we hope to see you there. Please also join us for our following workshops and ask more questions from Luke. And Luke, thank you very much for your time and workshop today. It was really, really great. Looking forward to the questions.
My pleasure. Thanks, everyone.
All right, so no questions for now. So then I think this is the end. Thank you.
Awesome.
Okay, thank you very much, Luke. Thank you, everyone.
So Sengali had a question for you there.
Right, yes.
And the question is, what's the best way for a client reconnected after offline for a few days to recap the events happened in the interim? For example, the user might need to know their kitten passed away thanks to Hunker during his absence, but nodes don't index events for a client. So the only real way that I know, so there's a few kind of ways to do that. The sort of straightforward way is that you need to sync the blockchain, right? And as you collect blocks, if you're a full node, as you're asking the network for the latest blocks, right, you're processing them one by one and processing each transaction. So that as you do that processing, you've built your own history of the events. Now, if we're talking about something, so if we're talking about a full node, it's kind of obvious how that works in the sense that a full node will always do all of the processing of all events and check everything that it does. So it'll be quite easy to know that their CryptoKitty passed away or whatever. The challenge comes when we talk about things like light clients, right? So a light client doesn't necessarily do all of the state transitions, doesn't necessarily hold all of the logs. And so as you mentioned, because nodes don't necessarily index events for other clients, then it's quite hard. Unfortunately, I don't think there is any way to do that in Ethereum 1.0 at the moment. There's definitely been some discussions around extensions to Ethereum 1.0 that might help with that. But I know that in Ethereum 2.0 that light clients are kind of being considered from the very beginning. And so the Wire protocol is likely to support additional features which allow you to ask other nodes for things like event logs and different sort of indexed events like that. And that should hopefully help support light clients. But of course, that's then a trade-off for security, right? If you've got a highly secure event that is like, oh, I received money for my boat or something, then you're probably going to want to do the processing and actually make sure that that thing's correct. Whereas a light client's typically going to trust some other peer on the network. Does that answer your question, Sengali? Would it be possible to use a distributed hash table for data that needs to be indexed and share the burden? Yeah, totally. Yeah, I mean, I don't see why a DHT wouldn't be useful for that. And I know that that there has definitely been discussions around that, especially with regards to the discovery protocol and the topics that you use. So maybe there'll be certain topics that, or certain nodes will advertise a feature where they will provide a historical index of events, for example. And so storing that data in DHT is definitely been talked about, and I don't see why it wouldn't be possible. It just hasn't been done in Ethereum 1.0 as far as I know, and it'll be very hard to introduce. I hope that answers your question. Thanks, Weiwu. Cool. No more? All right. See you later, guys.
Okay. Thank you, guys. Thank you very much. Bye. Bye, Luke. Thank you.
Bye. See you, everyone.